Well, I will give one example. Let us say what will be the factor of safety against the puncture of geotextile material from a sub-rounded, this diameter is 25 millimeter stone on the ground surface mobilized by a loaded truck with the infiltration pressure. Infiltration pressure P is equal to 550 kilopascal and travelling on the surface of the base course. So, we have to determine what will be the factor of the safety. And geotextile has the ultimate puncture strength is 300 Newton. This is as per ASTM D4833. So, you have to calculate what will be the factor of safety. So, we can use this equation, what is F required. F required, let us say equation P dash into D S square into S1 into S2 into S3. So, what is that P dash is 550 kilopascal. So, this is 550 kilopascal. So, this into dA is 25 millimeter. So, this is kilopascal I put into terms of the Newton. So, this will be the 1000 and dA is 25 millimeter. So, dA we can write 25 into 0.001 this square. So, Pi into d square S1, S2 and S3 value. This value we have to choose from this table depending upon the type of the puncturing object. For example, some value we can say it is a sub-rounded and relatively large. So, we have to adopt some S1 value, some S2 value and some S3 value from this table. So, let us say that S1 value is 0.55 and S2 value is 0.50 and S3 value is 0.5 and 5. So, knowing this value S1, S2 and S3 you have to substitute here. So, this if you multiply this, so this will be 0.55 that is for S1, 0.50 that is for S2 and 0.55 that is for S of 3. So, from this you can calculate F required this into this into this. So, this you will have that what will be the F required. So, this F required if you multiply this then you can have the value of 52 Newton. Okay. So, you can determine what is F required. Now, here you have to calculate that what will be the cumulative reduction factor. Cumulative reduction factor. So, let us say that cumulative reduction factor is equal to 2, equal to 2. So, the factor of safety Fs will be equal to F of allow divided by what is F of required. So, in the problem it is given that 300 ports. So, F allow will be equal to 300, this divided by factor of safety is 2, because this is the factor of reduction factor is 2. So, this F allow will be 150. Now, you can determine that Fs will be equal to 150, this 150, this divided by what you determine that F required is 52 Newton. So, F required is 52 Newton. So, Fs will be equal to 2.9, okay, which is acceptable. Okay. So, this is the puncture resistance. I talk you detail about this. Now, we will perform the brush strength test. So, main objective of this test to determine what will be the brush strength of a geosynthetic material. And brush strength is required to design the geosynthetics for separation. The geotextile may burst due to the applied upward load. For an example, this is the road and this is the stone aggregate. This is the stone, this is the stone aggregate. This is the stone aggregate. And you place the geotextile material. So, this is the geotextile material. So, this is geotextile material, you are placing here. Okay. And this is the subgrade soil. So, this is the subgrade. And when you apply the wheel load here, this is the wheel load you are applying on the load, wheel load. Okay. So, there is a tire. So, there is a tire implantation pressure, and this stone aggregate, let us say some diameter of the stone aggregate is dA, dV like this. Then when you apply the load, then due to the subgrade, so geotextile may push in the upward direction. That means there will be the pressure on the geotextile, and that pressure, let us say it is a P of G. For example, I am showing that this is the tire infiltration pressure, this is the pressure, this is the geotextile material, and this is the subgrade, and this is the PG is acting in the upward direction due to tire infiltration pressure is P of A, and this is the dB and this is the D of A. This is the stone diameter. Now, from this theoretically, from the concept, Giroud 1984 developed a formula required for the geotextile brush strength, and this equation for geotextile brush strength is as follows. This is T of required is equal to half into Pg into dB into epsilon g, half into Pg into dB into epsilon d. So, this is the required geotextile brush strength, where T required is required geotextile brush strength, So, this is the equation you have to remember to determine the brush strength of the geotextile material. Now, this epsilon g is strain in the geotextile. Epsilon g is strain in the geotextile. Strain in the geotextile. And it depends on the width of the void and also deformation of the void. Now, because epsilon g is the strain in the geotextile, it depends on the width of the void. Let us say W is the width of the void, width of the void. Okay? And Z of V is the deformation of the void, deformation of the void. So, you can determine what is epsilon G, that means strain in the geotextile material. So, epsilon G strain in the geotextile material can be written as 1 by 4 into 2 of Z of V divided by W by V plus W by V, this divided by 2 of Z of V. So, you can determine what should be the strain of the geotextile material. So, now what are the type of the equipment and accessory required for this test? So, you require that inflated diagram of the bursting tester, you require clamp and diaphragm, you require pressure gauge, pressure system and pneumatic instrumentation. So, this is a kind of experimental model. I can just show you. So, this is the equipment, let us say. And due to the burst, this geotextile material is like this. This is the geotextile material. And there is a pressure is P of B and this is D of B. So, this is the experimental model set up for burst strength. This is experimental model set up, model set up for burst strength in laboratory. So, this is the model setup. So, there will be the pressure from the bottom and this geotextile material may one time burst, and by the pressure you can measure at what strength the geotextile material is burst. This is very important, and also this is very important in case of the geomembrane material, that what should be their burst strength of the geomembrane material. And most of the time, particularly the geomembrane is exclusively used for the landfill system, and if there is a gas, and then there is a possibility of the bursting of the geomembrane material. It maybe looks like a balloon, it puts in upward, it bursts. So, one has to be careful that what will be the bursting strength of the geomembrane material. So, different types of the test also can be performed for the geomembrane material. I am just showing some of the type of the material that you can use. So, for example, that the different types of the test, and let us say that this is the Mullen burst strength, and you can see here is the circular clamp, and here is the geotextile over the geomembrane, and it has a dimension 1.2 inch. And then from the Mullen burst test, you apply the hydraulic load from the bottom and this geotextile membrane may pass. So, this is what you call the Mullen-Brush test. Then second, another type of the test, that what is called the ball burst. So, this is a kind of circular clamp and this looks like a ball. The geotextile or the geomembrane material is clamped and this diameter about 1.75 inch and this is the geotextile material. This is geotextile material. This is a circular clamp and then ball burst and you determine what will be the brush strength of the geosynthesis material. There are another type of geosynthesis material which you call the severe burst strength. So, this is the same what I mentioned, this is the circular clamp and this is the 2-inch diameter severe piston and this piston is applied on the top of the geotextile material here whose diameter about of this model is 6 inch and this way also you can determine what should be the brush strength of the geosynthesis material. So, there are different types of the geosynthesis material is available, but severe burst also widely used for the brush strength to measure the burst strength of the geotextile material. So, here also that some also the similar type equipment has been shown. Here what I shown you also this, and this is the severe burst strength. This is the Mullen-Brush strength as per ASTM D 3786, that is this one Mullen-Brush test, and this is the ball burst which is as per ASTM D 751, and this is the severe burst strength which we have developed in our laboratory, and severe burst is as per the DIN 54307E. So, this is different types of the burst strength test apparatus. Now, this procedure for this, you have to clamp the specimen, then you have to apply the pressure to the specimen until the geosynthetic fail. Average of brushing strength of each specimen is reported as brush strength of geosynthetics, and the unit of brush strength is kilonewton per meter square. So, one the calculation we are showing here, that when the geotextile is pushed up, okay, I am showing you that one calculation how to measure. So, geotextile is pushed upward and is form the hemispherical shape as well as fail due to the radial tension. So, the ultimate strength of the geotextile can be written as T of ultimate is equal to half into P of B into D of B into epsilon g. You know that where P of B is brush strength, P of B is a brush strength. Okay. And D of B, this is D of B, and D of B is the diameter of brushed equipment. Diameter of brushed equipment, and that is approximately 30 millimeter, which I shown you that brush strength which we have developed. And epsilon g is the strain in geotextile. So, I am at strain in geotextile. So, you know that what is the ultimate strain. So, you have to determine that what will be the allowable. So, this is the ultimate. So, you can determine T allowable. T allowable is equal to T of ultimate, this divided by cumulative reduction factor. This you remember, cumulative reduction factor, or you can say that CRF. Okay. So, you have to determine what is T allowable. Now, you can calculate the factor of safety. So, factor of safety, let us say Fs will be equal to T of allow divided by what is T required, that is T required. So, T allow is P of B into D of B into cumulative reduction factor into Pg into dV. Okay. So, factor of safety T allowable by T required from the earlier equation. For example, that if the dV, the diameter of the brushed equipment is known. Okay. So, I mentioned you that if dV is equal to 0.33 times of D of A, and D of B is equal to 30 millimeter. That is the diameter of the brushed equipment dB, and CRF, that is cumulative reduction factor, is equal to 1.5. So, there is a relation between the dB and dA, that is 0.33 times of the dA. So, you can determine what will be the factor of safety. So, factor of safety will be equal to P of B into D of B is 30, this divided by cumulative reduction factor. So, this cumulative reduction factor is 1.5. So, you can write 1.5. So, this into Pg and then into dV. dV has a relation with the dA, that is 0.33 D of A. So, if you calculate this, you can have 60.6 into P of B, this divided by P of G into D of A. So, you can have this factor of safety in this format. And from this you can make the design chart. This is the design chart for burst analysis of geotextile, considering the reduction factor 1.5 and the factor of safety 2. So, here this x axis is the pressure on geotextile stone interface in kilopascal. This is from 150 to 1950 kilopascal, and this is the required burst resistance kilopascal with the factor of safety 2 and reduction factor is 1.5. So, you can have the various line for the different diameter of the aggregate or stone. It may be 15 millimeter, 30 millimeter, 60 millimeter, 90, 125 millimeter, 150 millimeter, 200 millimeter and 300 millimeter. So, if you know that what will be the pressure of the geotextile stone interface, so then you can calculate the what will be the required burst strength. So, this design chart reveals that size of the stone aggregate possesses a significant impact on the burst strength of the geotextile material. So, from this laboratory you can determine that what will be the pressure on the geotextile material and what kind of the aggregate or stone diameter you want to use, and then you can determine what will be the burst strength of the geotextile. Thank you.